Hello, good evening. Uh, can you confirm if my screen is visible? Okay, I think we'll start now. It's about time now. So, good evening. I welcome you to this fifth session of our discussion on doubt, our discussion and doubt session on basics of finite element analysis, part one. And until last week, we covered that the related method and weighted residual method, and started with the finite element method formulation. So there was some basic difference we discussed in the last class. Would you like to remind me what was the basic difference between the finite element method and the other methods we discussed so far? Okay, we have another participant. So, anyways, I'll start. So we let people join. So, until last class, we studied the weighted residual method and then started with the finite element method. So, the basic difference between the FEM and other method was that in FEM we discretize the domain. The main difference lies in the fact that the in FEM the domain is discretized, and the number of equations coming up mainly depends on how we discretize the domain, how fine the discretization is. So we studied how weak form is converted into equation for each element, and then we even studied the transformation of coordinate system from global system to an elemental system. So we'll again revise some basic steps on how we proceed with FEM. So first we write the FEM starts with writing the weak form, and we write the weak form for the elemental form. And after writing the weak form, we estimate the solution vector as G. So this is the sorry. So this is the value at nodes. And these are shape functions which are known, and these are unknowns. And we estimate the weight function as, so we'll take the same shape function as the primary variable for the weight function. So we'll get the elemental form something like this, and this would finally give us some equations which can be represented in the form of matrix and vectors. So then we will have transferred, since to make the process common for each element, we'll have to transfer the global coordinate system into local coordinate system, and we discussed this in the last class. So for uh, for some given differential equation, we'll have the matrices coming in the form like of this, if we take the linear functions like this, and if we take the quadratic shape function, we'll get the matrices in this form. So this was just one trial. It was shown in the class. Depending on the type of problem, we can have uh, any type of matrix and vector, but this general structure would remain same. If that is the reason we take elemental coordinate system. So every time for every element, we'll get the same values. And then we studied the okay. Then we had to study the assembling of elemental equation. Okay, so we have suppose we have a domain in the form of this here, and so we discretize it into three elements, this one, two, and three, and so total we'll have four nodes if we take linear elements, and so for each element we assign elemental nodes. This one, two. For each one, we'll have one, two, and one, two. So thus for each element we can write the required matrices and vectors in this form, and there are certain conditions that need to be satisfied in order to compile all these uh, elemental equations. So the first condition is the condition of continuity. So we know that if we have this domain here, and suppose this uh, node 2 here is shared by two elements. So elementally this is 1 and 2, and for element 1, for element 2 also is 1. So node 2 is shared here. So that whatever displacement here is at node 2 should be same on both the sides. So uh, for element 1, the second node, second elemental node is same as what is for element 2, the first elemental node, and we just assign them some common name too. That's how we do here. So here if you see, we replace all the u values here. So u values here, we equated these two, and likewise we equate these two. So depending on which node is shared, we assign them the same value. So here 2 is shared, and likewise 3 is also shared between two elements here. These two are shared. And so this way we'll have the same value for u in these equations. And for the second condition is the balance of force. So at a shared node, the net forces are summed up. Okay, and so if we consider the f vector here, we'll add up. So for whatever the contribution is on 1 here, so at node 2, whatever the contribution at for node 2, whatever the contributions is here at node 2, we'll have the same. We'll have we'll have to add up the contribution from both the two elements, and that's what we get here. Similarly for the other shared node 3. And regarding the point forces, so when we discretize the domain, so suppose we discretize it here as this, we have node 2 shared. So we imaginarily we break this each element. So these are elemental coordinates. So when we break so even in a mechanics problem, when we break some rigid body, we have some equal and opposite forces coming at each node. So we assign some value q1, 2, and q. So in nature they will be equal and opposite, and thus we have this condition. So this is the way we assemble the elemental contribution for to get the our global matrices and vectors. So at the end we have four displacement variables which are unknown, and we have two q values which are unknown. So we don't know. So suppose this is a deformation problem, deformation bar. So uh, we have u1, u2, u3 coming up here, and q1, q2, q3, q4. So based on problem, if we see that there are no point loads assigned inside, so we know these terms are zero. But these six values basically, so basically we are left with six unknowns and we have four equations, right? So to solve this problem, we need boundary conditions. So that is why boundary conditions are necessary to solve any problem. Otherwise, we don't have a definite solution for the given equations. So suppose if we are given both sides as essential boundary condition, then we know this term and we know this term. So now only unknowns are left are these four. Okay, and likewise, if we are given any essential boundary condition on any one side, then also we'll be left with four variables. So we need boundary conditions at both the sides. And once we are done, we get the boundary conditions. We get four unknowns and four equations. Then we can easily solve this. So we'll see how we'll solve this later. Okay, so there's one more condition we discussed. So like in earlier discretization here, we had the nodes were coming in sequence. We had two after one, three after two, and four after one, four after three. So it's easier that the neighboring values follow nodes follow continuity for each elemental contribution. But this wouldn't be so trivial in such cases where the nodes are not in a straight line. So we have this system of three bars which are connected with this rigid plate. So we have a rigid plate here. So rigid plate means there won't be any deformation here. So this whole plate should stay in one place, and whatever the deformation of one point would follow by the all the other points of this plate. That's why we assign 0.3 everywhere. So we see that the for the continuity condition is different for this case based on how the configuration of the system is, and likewise the force balance is also changed here. So we need to look at the way the domain is described in the problem to solve these problems. So one thing we would need for this assembly is the connectivity matrix. So for 1D case, this is quite trivial. We see the configuration, and we can easily assemble the elemental matrices to get the global matrix. But for 2D and 3D case, this connectivity matrix plays an important role. So we'll here just for the sake of understanding, we'll see it for the 1D case. So basically, this connectivity matrix B basically each row in this connectivity matrix represents an element, and each column represents the elemental nodes. So we have, so I'll write elemental nodes and one. small n2 like that. So it basically and the values that we fill inside are the values of the global nodes. So we can connect where the global nodes are meeting the elemental nodes. So you would see. So for example, if we have simple case, we have two elements, we have three nodes. So for this case, how we write its b for element e1, we have this is our first elemental node n1, and this is the second elemental node. So okay, I have written 132 deliberately to get some different. So there's no hard and fast rule on naming the nodes. It's easier if we do it like 1, 2, 3, but there's no rule limiting us to do otherwise. For second element, what is the first node? So then one. So we can write 3, 2. This is our B for this case. Suppose if we have two elements, but we have used quadratic. This is our element one. This is element two, but we used be using quadratic element. So how should we look for this case? So again, the number of rows is the number of elements. So we have E1, E2 there, and for each element, the elemental nodes will be like this: N1, N2, N3. So it will be 1, 4, 2, and for this element will be N1. So this would be 2, 5. So this is the formula we had, right? The order of B is the number of elements times uh, order of elements plus 1. So this is the size of the matrix. So this is basically a 2 by 3. Okay. So there were some general observations we had in this whole process of FEM. First thing is that use containers. Suppose we have so if we get some value u1 here, u2 like this, u3 like this. So since we ensured the condition of continuity, whatever solution would be continuous with respect to value of u. But this is continuity is not ensured if we take the derivative of u. So for the same thing, so for linear element we have constant value of derivative, right? So this would be a negative slope. So we'll have some negative value, constant negative value. And for the next element, we'll have some positive slope here, so we'll have some positive value. So there's no continuity ensured for the derivative of u. So that is why the convergence is easier for this primary variable than this secondary variable. Okay, okay. We'll just skip this first. So then we started with the radially symmetric problems, and there's nothing. This is actually not even relevant to FEM PLC, but there was some aspect that we need to see with regards to FEM. So if we have any circular radially symmetric problem, we can easily convert into a 1D problem. So we don't need to look it into a 3D way. So we can just consider a one dimension, that is the radius, and we can easily solve the problem with respect to one variable. So we get a differential equation. We know the differential equation for this problem would be like this. But one thing we need to do is to take the to get the weak form. We need to do the integral over volume, since integral is always taken over the domain. So so there is a way to reduce this integral over volume to 1D integration, and that's what we studied here. So this would basically give out some extra terms into the weak form, but that's nothing new. We'll after that, after getting this weak form, the process is basically the same. We get the shape function, and we write the solution u as uj psi j, and we get the weight function as psi I, and then the getting the algebraic equation, writing the matrix vectors. Everything is same. The process is completely same. There's one the only thing we need to take care about is taking the volume integral for this case. And then we started with the 1D heat transfer problem here. So heat conduction, the basic 1D heat conduction equation is just similar to what we studied in the 1D bar problem. The we just name the some terms that are coming up differently, but the basic structure of the equation is same. So we studied it for the Cartesian system, cylindrical system, and spherical system, and then we even studied the convection term for this. And for steady state, we'll have some equation where we won't have the time derivative term. And again, after getting steady state equation, there's nothing different, nothing unique about the equation. We have seen these equations before. We'll just take whatever the variable terms are together. So t is our primary variable here. And we have minus a minus p beta t. This is the constant term. So this whole thing can be taken as f. And so now there's nothing unique in writing the weak form from here, and we'll get the same elemental equation, same matrices vector terms, and then after that everything is same. Whatever is studied for the 1D bar problem. So I guess that was it for this week. For this is the content for the first week. So if there's any doubt, I can take it now. Otherwise, I can proceed to solving some problems regarding this. So there's no doubt. Okay. Okay. Thanks. I'll move forward. Okay. Okay. So find the elemental force matrix if the applied distribution load for the bar is 6x. So if we write FIS, so this is our linear term for the force matrix, right? Elemental force matrix. So we know this value of Q here, that is 6x here. So can someone tell me what are the shape functions we are going to use? So we'll take for linear element. So what should be psi 1 and what should be psi 2? Can someone tell me?
x minus xa by he.
X minus xa for which one? 1. I think it's
1. Yeah.
x minus xb upon he. And for 2,
Xa minus x by
upon. Yeah,
he.
right, right. But there's one more formula for shape function we studied. 1 minus g. Why can't we use this one? Sorry.
This is for local coordinate, I think.
Yes, right. Exactly, exactly.
Yeah.
So one thing that I missed in this question is that I didn't tell which coordinate system we need to follow. Okay. So since we don't know even the position of nodes, then we'll follow this local coordinate system. So because for local coordinate system, we know the value where it starts from 0 and we'll consider he to be 1. Say. So for element, we'll follow the local coordinate system. We integrate between 0 to 1, 6x, and we have psi. Okay, so we have f1 as 1 6x 1 minus x. That gives us 6 minus. So we get 3 minus 2. 3 minus 2. For f2, we get so we have 6x cube upon 3. We get 2. So our fi would look like this for this specific term. Okay. And I suppose we even had formula. Let me check. can just verify with the formula. QEH formula I think won't work because Q isn't constant here. Q is a variable. You can't directly use a formula here. What if we use the global shape function? We use one. For 0 to 1, this would be G. Okay, we get the same function, of course. Okay. Anyway, we'll move forward. Okay, let's transform the stiffness matrix for 4 nodes into condensed form of value solution not for. Okay. So, if we have a 4 node matrix, what should be the size of a 4 node matrix? Can anyone tell me? Anyone? Or what should be the size of the stiffness matrix for 4 nodes? The global stiffness matrix. Would anyone like to answer?
First row will be 0.
Oh no, my question is what should be the order of the matrix for 4 nodes?
4 by 4.
Right, right. So we have 4 nodes here. So we'll have some K11, K12, K13, K14, 21. So I just not write the symmetric terms. 2, 3, K, 3, 4, K5. I'm just omitting the symmetric terms. And what we have is we have 4 nodal values here. So this is equal to some force vector 1 F2 4. So we're not talking about let's not talk about the q values here, we'll ignore it. So the question is basically if you know the maybe you know the value u1, this is known. How do we transform this uh, this metric, these system of matrices and vectors to finally get into the some form which we can solve to separate out the variables and unknowns. So basically, someone just said that we need to eliminate the first row, first column. So yeah, right, that's the way it is done. Basically, we'll just eliminate this whole thing here and this whole thing here. So we'll be left with a 3 by 3 matrix and 3 column vectors. So the matrix remains unchanged. I mean the elements remain unchanged. 3, okay, 3, 4, 4. And here also we'll be left with u2, u3. Since u1 is known, we don't need. But there's change that comes into this first term. So suppose we see, if we write the equation 2 here, you can write it as k21 u1 plus k22 u2 plus k23 u3 plus k24 u4 is equal to f2. So how we arrange the equation is that we take the unknown values on one side, known values on other side. So we have these unknowns u2, u3, u4, and since u1 is known, so we switch it to other side. K22 u2 plus k23 u3 k24 u4 f2 minus 21 u1. Okay, so now it's simple, right? We can arrange in form of vectors k22 k23 k24 minus u2 u3 u4, and on the other side we'll just be left with f2 minus k21 u1, right? So we have the first, this is our row, and so this is this row 1 here, row 1, and we have this. So corresponding to this row, what element we have in this vector, f2 minus k21 u1. And similarly for other equations also, we'll subtract this term. So for this one we'll have k31, I guess, yeah. k31 u1, and here also we'll have k41 u1, right? Okay. Okay, suppose there is some value q here, this, so which is unknown. Can someone tell me how will we find this q value here? I hope this method was clear. So why I am arranging this in terms of in form of matrices and vectors, that it is easy to solve in terms of matrices and vectors. So in computer programs we solve the algebraic equations in form of matrices and vectors. So it is important to know how to reduce your uh, global matrices and vectors after applying boundary conditions. So this is nothing but everything is after applying boundary condition. So now if this is clear, can someone tell me how do we find this value of q here? This one. Q is basically some external load applied at Q, or yeah, some Q, some point load. If we talk about the bar problem. Would anyone like to answer? So if we have this Q unknown here, we'll add this Q to this term here, right? So basically, the first row which we eliminated here, we'll write this. So we have K11 U1 plus K12 U2 plus K13 U3 K14 U4 F1 plus Q. So after solving these equations, we'll get the value of these or this vector. So we know u1, we already knew u1, we know u2 now, we know u3, we know u4. So everything on the other side is known, and even f is known. So we are just left with one unknown here. So we can easily find q here, right? So likewise, even if we had q on the other end, we can easily get this. So on each boundary, either the value of u would be given or q would be given. Even here also, the q would be given or u would be given. So in that way, you can first find the u values and then find the corresponding q value. Okay, I hope this was clear. Okay. Okay. So this is the same problem that is given that was shown in the class. This is the rigid plate, and these are deformable bars connected to fixed end, and these three bars are connected together through this rigid plate. So would now someone else answer this? How would we write the connectivity matrix for this problem? First of all, what should be the order of connectivity matrix? Yeah. Someone please answer this. What should be the size of this connectivity matrix for this problem? Please feel free to unmute yourself, or you can type in the chat.
So connectivity matrix is B matrix, sir.
Yes, yes.
Uh, so first of all, first element, uh,
First, tell me the
node.
order of the matrix. I mean the size. What cross what?
Uh,
So how many
2 plus
number?
3.
So how many number of rows should be there?
So three number of rows should be there,
Yes.
and two number of columns.
Right. Right. So for each element we have one row. For each elemental node we have one. So what should be the entries of first row?
So first row is considering the top as one first element, two and three
Okay.
for first row,
Right. And then
and next at bottom, considering the bottom beam as second element, one and three are
fine. Good. And then for third one.
for third one it is three and four, sir.
Okay. Good. That's right. So yeah, we have this connectivity matrix for the system. Now for second case, we have I've taken a 2D domain. So although this was not taught in class, but I thought this would be an interesting exercise to understand the importance of connectivity matrix. So we have two elements here, and so first of all, tell me what should be the order of the connectivity matrix. What it should be the size of the matrix. Would you guys like to answer this?
So two rows and three columns, sir.
Right, right. Because we have three nodes for each element. So, we'll assign an anti-clockwise direction for each element. So in that way, we'll go as one elemental node one, elemental node two, elemental node three, and for this one also one, two,
Two and three.
yeah. So yes. So what should be the entry for first row?
Sir, one, three, and two.
One, three. So I have assigned this as a three. This is my elemental n3. So n3 means my elemental third node.
Yes, sir. Sir,
So
but I am
okay,
telling
sorry,
about
sorry.
first element.
Okay, sorry. Yeah, okay. So that would be one, three, and two. Right. Sorry, my mistake. So what do we?
Next one is one, three, four.
Okay, 134 or 143.
Ah, sir, 143. Sorry.
Uh, okay, good. That's right. So when you start doing the 2D problems, then you will understand the importance of this P matrix. So basically, when we have to assemble the stiffness matrix for each element, uh, in case of 1D, if the nodes are arranged in linear fashion, it's very easy. One, two, three, four. We just have it. So we have two common here, three common here. So yeah, when we write stiffness matrix here, so at two we know we will have to add the contribution from each element one and right. So this is very trivial, but in case of when the configuration is not linear, like for this A problem and of course for 2D and 3D, we face difficulty while assembling these elemental nodes. So that's why we prepare this connectivity matrix. Okay, so I hope this was clear. Okay, find the global stiffness matrix for part A. No problem. So first of all, we'll assign we have three elements, right? So we'll for each element we can just use this notation for each element. So we say ith element 2 1 I. So what we need is the global stiffness matrix. So how is the 2 3 4 3 3 4? So B in this case is 2 3 1 3 3 4. Now we'll see how we can get the global stiffness matrix. Okay, global. So we have 2 3. So since we have 4 nodes, we'll have a 4 by 4 matrix. So what should we have fill in this first entry? 1:1. Can someone answer? So we have 1 2. So globally, for node 1, we have contribution from element 2. You see here, node 1 comes only in element 2. So 1:1 would be K1 1 1 and 1 2. Do we have any contribution in 1 2? No. So because we don't have any connectivity between node 1 and 2, so we get 0 in this. And for 1 3 we have for element 1 2 we have K1 2 1, isn't it? You're getting it for the connectivity between 1 and 3. 1 and 3, that is given by this position of 1 3, that is available only in element 2. Okay, so that's why we have contribution from there. And for 1 4 we don't have any connectivity, we assign them as 0. So for 2 we have a yeah, for 2 we have contribution from element 1, and 2 is the first node, right? So we write this as this. So I'm skipping the symmetric terms. And for 2 3 we have contribution from 2 3. We again have from 1 K1 2 of 1, and 2 4 there is no connectivity. For 3 3 we have contribution from two terms. So 3 is present in 2 elements, here and here. So we have from 1 and 2, and 3 is always the second node, so we have K2 2 every time. This one is from 1 and this one from 2. And 3 4, do we have connectivity between 3 4? Yes, we have from this E3. 3 4 is 3, 4 is basically k 1, 2 or 2, 1 of the third element, right? And of course for 4, 4 we have a contribution from element 3. Okay, so you see, this assembly was not so easy if we just look at these nodes, the figure, and just try to assemble this. So that's where this B matrix was essential to formulate this global K matrix. So I'll just check if there's anything missing in the symmetric term. So yeah, 1, 2 will be 0 again. 3 to 1 is, yeah, the same symmetric terms. Okay. Yeah, so this way we can develop the global matrix based on uh, this what do we call it, connectivity matrix. And can we find the global F also? Suppose for each element Fi is given as F1i, F2i. So how should we write this? So we'll of course have four contributions. We can in the first one we have the contribution from node 1, and that node 1 is global node 1 is present in the first node of the second element. So this would be this. And for global 2 is present in the first node of the first element. So we write this as F1. Okay. And for 3, global 3 is present actually at 3 places. So I need to erase this. So 3 is basically the second node of element 1. It is also the second node of element 2. And it is also which is the first node of the element 3. Element 3 is first node. And F4 we have, F4 is basically the second node of element 3. Okay. So this is how we can get the force matrix also. This is the way of assembling these things from elemental level to global level. I hope this was clear, and if there's any doubt, you can ask now. Is there any doubt bit from this question, or even from the whatever we covered for the summary of the last week? Okay, let me know if there's any question, or if there are no questions, we can conclude the session. So yeah, okay. Thanks, Vijay, for confirming. So there are no questions, then we can conclude the session. Okay, thank you everyone for your patience, and I hope to see you again in the next session. Till then, keep learning.